Hello everyone, my name is Thierry Chekam, as was introduced before. I am affiliated with the SCS and the University of Luxembourg. I will present our paper titled Killing Stubborn Mutant with Symbolic Execution. It was published at ACM TOSEM Journal last year. This work was performed with Mike Papadakis, Yves Le Traon, Maxime Corday. In a nutshell, this work tackles the problems of automation of test input generation for mutation testing. Mutation is a test adequacy criterion that uses artificial folds, also known as mutants, to measure the quality of test suits. And the coverage measurement by a test suit using mutation on the mutant is computed by executing the same test input on both the original program and the mutant and checking the outputs. If the output differ, the mutant is said to be killed by the test. And the ability of a test suit is then measured by the proportion of mutants that it can kill. Now, to perform mutation testing on the program on the test, mutants are generated by systematically making simple syntactic changes on the program. Then existing test suits are executed with each of the mutants, and the kill mutants are recorded. If the proportion of kill mutant is below the given threshold, additional tests are generated to kill the remaining mutants. Sorry. And now if the mutant that now remains after the generation, after the execution of the mutants are called the stubborn mutants. And additional tests can be generated to kill those stubborn mutants. So the focus of this work is basically to generate this additional test to kill the stubborn mutants. So let's look at the conditions to kill a mutant. In order to kill a mutant, a test input need to be executed both on the original and the mutant. And then the test need to reach the point where the mutation occur. And at that point, the test should make the state of there should be a difference between the state of the mutant and the state of the original program after the mutant is executed. And then that difference need to be propagated to the output of the program. So now, how do we use symbolic execution to generate tests to kill mutants in an effective way? So we first look at the basic way of generating tests to kill mutants. Let's say we have here on the left side the symbolic execution path tree of the original program. On the right side, we have the same thing for the mutant, which is at the location where you see the M1 there. And now, in order to generate tests to kill this mutant, the basic approach is to do this kind of symbolic execution and get the trees. And then for each path, we compare the path condition. We need to find two paths such that the conjunction of the path condition is feasible. And at the same time, there's a difference with of the outputs of the test execution following those paths. And then we can say that the mutant is killed because the outputs differ. So if we have that, if we can now do the symbolic execution and get this path condition and the state, which is like at the output, the variables there, and then we have this kind of formula, we use the constraint solver, we solve it. If there's a solution, then that would be like a test input that will kill the mutant. So the problem with that kind of doing is that it's very expensive, since symbolic execution already is kind of expensive, plus mutation. If you have many mutants, it becomes very expensive. And the other technique that exists in research, what they do is that instead of doing symbolic execution to the output of the program, the symbolic execution is stopped right at the point of mutation. And now the condition will become still like the prefix of the path condition of the path condition at the point of mutation when we do the symbolic path exploration. And instead of using the output to compare the original program and the mutant, the state at that point is used instead. And this can help to reduce the cost of the symbolic exploration, path exploration for the mutants. But now one of the problems with that is high probability of not killing the mutant because of the failed propagation. So a test can be generated and the test don't actually propagate the difference to the output. I will show it with this example. Let's say we have this simple program, and I just simplify it by showing on up here the path, the symbolic tree, the symbolic execution path 3 for a small, the part of the program that actually has a mutation. So we have here statement 2, statement 3, at statement 4, at statement 3, where the mutation is, the path condition is x0 is less than 0, and the symbolic state is the variable x has x0, which is like the input, and n equal to 0. And after the execution of statement 3, we will have two different states for the mutant and the original, because there's the mutant that will change the statement here. Instead of n equal to x, we have n equal to x plus 1. So here the state has changed, and we have here x0 equal n equal to x0 plus 1. Now, if now we try to generate a test at this point using the formula that I previously shown, we will have something like this, where the state of the original will be x0, because n is the only thing that is different, basically, and is the value of n that is compared. So you have x0 should not be equal to x0 plus 1, and the path condition is the same, x0 less than 0. So when we solve this one with Z3 solver, we get x0 equal to -1. However, if we execute this, the original program with x0 equal to -1, and the mutant with the same input, we get the output is 0, 0 for both. Then the input actually it does not kill the mutant. So what we can do then is to kind of propagate a bit further by doing a bit exploring the path a bit more, and we will get something like this with the original. If we continue the execution with the original, we will get an invisible path, and also if we consider the n, the then side of the if here at line 4. We will have this one. We add this to the path condition, which is x0 is not equal to 0, and the state has not yet changed. And when we get to the line 7, we will have n is updated to x0 plus 1, because we have n plus plus. And if we do the same thing for the mutant, we will get something like this and this one. So we will have these two paths, where you have one has path condition x0 not equal to -1, the other one x0 is less than -1. And the states will be x0 plus 1 and x0 plus 2. Now, if we do we try to make to solve that formula that I showed before initially at this location, so just before the return statement, what we will have is that for this path, we will get this formula. And if we solve this one, is infeasible. And now if we try to compare the original program path with the second mutant path, we will get this formula, which actually with Z3 solver, we get -2 as a solution. And if we execute the original program and mutant with -2 as the test input, we actually see that the outputs are different with the original and the mutant is actually killed. So this shows that it's important to propagate a bit further the symbolic execution in order to increase the chances of killing a mutant. But there's a problem, of course, that if we propagate more, we actually need more resources to do the symbolic execution. So what we propose here is a technique that kind of helps to balance the two, to balance the increase the chances of killing a mutant while also controlling the cost of the symbolic execution. And we achieve that by proposing a set of heuristics to the symbolic execution, which are the following. So if we have here the symbolic execution tree, I just make an abstraction of it. With here, the red one is like a mutant at that location. So what we propose is like an heuristic to control how to reach a mutant. So instead of just starting from scratch with the symbolic execution, we actually use existing tests that we had before, and because we try to execute the mutant and we are not satisfied and we want to generate additional tests. So we can use the previous test to kind of use it as seed for the symbolic execution and guide it towards some parts of the program. So that's one of the way we control it. And the second way to control is that we add checkpoints at different locations of the symbolic execution tree, so that at those checkpoints, we can actually compare the states of the original and the mutant program. And this can be set by the user depending on the type of program and so on, so that the propagation can actually proceed onto the checkpoint instead of just right after the mutation. And also we have some heuristic to prune the paths after the mutants in order to kind of select the path that might be more important. So we have strategy like randomly select path that will prune, or select the path that are closer to an output, like printf or something like that, based on the static analysis. And we also propose a way to kind of reduce the cost of the symbolic execution by merging the symbolic execution of multiple mutants into the same symbolic execution to some extent. So let's say we have two mutants at certain point of the symbolic execution. Here at line 3, we have these two mutants. The symbolic execution before that, it can actually be shared by the two mutants. So what we do is that we create a program where we kind of embed all the mutants in the same program with the switch. And then the symbolic execution, when it reaches the switch, then it will actually make a fork with the different mutants. And this way we can actually save some cost of the symbolic execution in the dimensions of the mutants. So we implemented CMU on top of KLEE by adding and modifying around 8,000 lines of code, and it's available at this link. So now for the evaluation, we compare the ability of CMU with KLEE and the technique that were proposed in the literature. And the subject program that we use at 36 program from GNU Core Utils. So the procedure for the experimentation is the following. We have the tests that are coming with the programs, and we generate some tests using KLEE by targeting.
Excuse me, Thierry, you must take care of time. You are already a bit ahead, so try to conclude quite quickly.
Okay, sure. Thank you. So we generate additional tests with KLEE, and we have an initial test suite. Then we execute the mutant to see which one are killed, which one are not killed. And we apply each of the technique to kill the remaining mutants, basically. And then we execute again to see how many are killed by the test that we generated. And the results are the following. We see that with the CMU actually kills around 37% of the stubborn mutants, while infection only kills 17%. So this shows that we actually have some improvement. And we also compare like per program, and we see that there are some cases where KLEE, for example, killed some mutants that CMU could not kill, and this is mainly due to the large number of mutants. And there are also some places where infection only could kill more mutants than KLEE. But overall, than CMU, overall CMU generated more mutant killing tests than infection only. So overall, we in conclusion, we have the problem of generating tests to kill stubborn mutants. We propose, we see that the approach in the literature is kind of limited, and we propose some heuristic to kind of further the propagation, and we implement it into a tool, and it actually kill more mutant than the approach in the literature. Thank you.